x equals to 0 gives f of 0 equals to 0, right? And x equals to -1, it gives f of -1 equal to undefined. So the sign chart for the function itself, kind of boring, 0. Actually, let me make it a little bit bigger here. So here's the sign chart for the function. There are two things of interest, -1, 0, right? And we can try plugging in some numbers. Plug in like 1, it's positive, right? Plug in, say, -0.5, you get negative. Plug in -3/2, you get -2 even. Let's say you get negative. So it's either negative to the left of 0 or it's positive to the right of 0. All right. In fact, what is x equals to? I said x equal to 1. What's wrong with me? X equal to -1. X equals to -1 is a vertical asymptote, right? Okay. So consider the derivative, df dx. What's that equal to here? What are we going to do? Looks like we got to do quotient rule, right? So we're going to do dx dx times 1 plus x quantity squared minus x times d dx of 1 plus x quantity squared divided by 1 plus x squared squared. That's the quotient rule. It just so happens the denominator already has a square on it, so we end up with a fourth power in the denominator after the rule. So we've got 1 plus x quantity squared minus x times 2 times 1 plus x quantity, all divided by 1 plus x to the fourth power. So we're doing analysis past the point of the differentiation. It's in our vested interest to simplify if possible. I would point out here, there's a common 1 plus x upstairs that we can factor out, right? So what I would do here, I say, okay, well, this is 1 plus x times 1 plus x minus 2x divided by 1 plus x to the fourth power. So I can cancel, I can reduce one of the ones in the denominator, and I can get myself looks like I can get myself a 1 minus x divided by 1 plus x cubed, yeah? Which looks a whole lot nicer than our second line, doesn't it? Like, it's a lot nicer. So what you should see as you look at rational functions, right? This is a rational function. And so if a point is not in the domain of the original function, that point is also not going to be in the domain of the derivative, in the second derivative. So like here, the fact that -1 does not exist in the domain of f means that -1 is also not going to exist in the domain of the derivative of f. And we see that in the formula, right? So that's just something kind of to anticipate. And so what are critical numbers of the derivative? Well, critical numbers of the derivative, they're going to include the points which were not in the domain of the original function, and they're also going to include possibly points where the derivative is 0. Where could the derivative be 0 here? So c equals to 1. It's a critical number because f prime of 1 equals to 0, right? And also, c equal to -1 is critical number. Oh, see there, did I actually say last class that c has to be point in the domain of the function to be a critical number. Like, I probably shouldn't say that. If I have said that, I need to unsay that. Because we definitely want to allow the case that the critical number is not in the domain of the function. Otherwise, we'll get into trouble with the analysis. Because we definitely want to put -1 on our sign chart for the derivative. So let's do it. Here it is. So we got -1 and 1. And let's see here, how's this work? If you plug in 2, you get positive or negative? We get -1. Yeah, we get minus. What happens if we plug in like 0? We get a positive. What if we plug in -2? Like negative, let's say plug in -2. What happens? You get negative? Yeah. So you notice the difference. I mean, I'll put them both here. Here's f of x, right? So the funny thing is that the function looks like it stayed negative at -1, right? But it's funny to, I'm sorry, this is 0. Got to be careful. The places where the function is not defined are the same places where the derivative is not defined. However, the places where the function is 0 and the places where the derivative is 0, they differ. The function is 0 at 0. The derivative is 0 at 1. Okay? Now we could... Sadly, we do not have enough time to study concavity for this function. Concavity is going to cost me another 3 minutes to do carefully. We don't quite have that much time. So I'm going to let you guys study concave up, concave down for this. Let's just work on the graph. So what does it look like? So where is it increasing? Increasing on -1 to 1 is decreasing elsewhere, right? And so it's got an x-intercept where? At 0, right? Got a vertical asymptote at, right? X equal to -1 is vertical asymptote for this thing. Can you guys tell me how the limit at plus or minus infinity works for this thing? We haven't really looked at that much in this class yet. We will get to that in about, like after we get past the max-min stuff, I'm going to turn back to look at limits at infinity for a couple days. We'll learn something called L'Hopital's rule. But this one, because the denominator has a larger degree than the numerator, this limits to 0, both going to plus and minus infinity. So like I know it's going to go to the x-axis eventually. So what's going on here? It's decreasing to -1. So I think what happens here is it's decreasing to -1, right? Then it's increasing on the other side of -1, right? So it must do this. The graph must do that because it's decreasing and then it's increasing, right? It's negative before 0, so it has to look something like that. And what happens at 1? What's f of 1? It's 1 over 1 plus 1 squared, which is otherwise known as 1/4, right? The 2 is squared, though, right? Is that a local max or a local min? Well, Well, it's going from, the derivative is going from plus to minus. It's a local max. So if we get over here to like 1, go up like a quarter, it's got to do something like that. And then I'm telling you that it goes down. I'm not, the graph is not very good, right? So this is actually an example of a function that it would be nice to calculate the second derivative, because the second derivative would tell us where these points of inflection are. Do you guys see where there's going to be a point of inflection? Well, it's not exactly a point of inflection, but there's going to be a place where concavity changes. Actually, maybe not. It's going to be concave down here, don't you think? Concave down here. I think it's going to be concave down right up until about like, there's an inflection point somewhere in here somewhere, right? Somewhere in here there's an inflection point. We could find out where that was if we wanted to solve f prime prime of x equal to 0, we could actually find where that is, right? But our time is up for today. Any questions? So your homework, mission 6, is due Wednesday. If you have a question, I can answer it.